Welcome to MindMentors. Let's solve this gnarly integral. So what we have here is the integral from 0 to pi by 2 dx over the square root of sine x plus the square root of cosine x, all inside parentheses raised to the power of 4. So upon first seeing this, I guess the first intuition could be to expand this, to expand the denominator. So if you remember the general formula of a plus b to the power of 4, it goes something like this. A to the power of 4 plus a4 a cubed b plus 6a squared b squared plus 4ab cubed plus b to the power of 4. So if you put a as square root of sine of x and b to be the square root of cosine of x, we can expand the denominator as follows. So square root of sine to the power of 4, that's just going to be sine squared x plus 4 sine of x, square root of sine of x, times square root of cosine of x, plus 6 sine x cos x. Plus 4 square root of sine of x cos of x times square root of cos of x plus cosine of squared x. Okay, so when I do this, I see a familiar term right here. Sine squared plus cosine squared. Well, according to Pythagoras' theorem, this is just 1. Because if I were to draw a triangle, and I would consider the unit circle, you could consider the hypotenuse to be of length 1. So this, the base right here would be cosine of 1 times cosine x, considering this is x degrees, and this would just be sine of x. So we could just say that cosine squared plus sine squared is equal to 1. So this would simplify to 1 due to Pythagoras' theorem. And if I look at this more closely, I have this, this, and this. And if I write this out, I'll just take the square roots together. This looks really complicated to integrate right off the bat. But we also have to consider that what makes this even harder is that this is on the bottom. So this is the denominator. And I don't know any good u substitution or somehow making use of our bounds to actually integrate this. So maybe you could perhaps do this with some sort of trig identity and probably use some sort of more advanced tricks to compute, but I feel like it would be way longer than what needs to be done in order to solve this problem. So instead, let's try to take a better approach at the problem. So we are given the integral from 0 to pi by 2 d of x over square root of sine x plus square root of cosine of x raised to the power of 4. Well, what I can do immediately is to see if I can somehow take this, try to get only one trigonomic function to appear inside this, inside these parentheses. So what I can do is I could try to take cosine x, square root of cosine x out of the parentheses, and I could do it as follows. So I can write this as square root of cosine x times square root of sine of x over square root of cosine x plus 1. all raised to the power of 4, because when I expand, if I were to FOIL this out, I'll still get back the same thing. So proceeding onwards, I can write this 2. And since this is square root of cos of x to the power of 4, this would actually be cos squared x when it comes out. And inside, I have root sine of x or root cos of x. That's just root tan x plus 1, all raised to the power of 4. So this would become 0 to pi by 2. And if I look carefully, there's a cosine squared x on the bottom. And I could take this to the top and I could just write secant squared x dx over square root tan x plus 1 to the power of 4. So let's see if I can make some sort of a substitution right here. And the substitution I want to make is let tan x be equal to u squared. And the reason I want to be u squared is because whenever I put in u squared into this square root, I can get back u plus 1. So if I let tan of x be equal to u squared, if I were to differentiate this, I would get back secant squared x dx is equal to 2u du. And I can see that this term right here is already present on the top right here as well. But I'll have to change my bounds of integration though. And if I plug in pi by 2, tan at pi by 2 is not defined, but since we're approaching pi by 2 from the left endpoint, I could say my endpoint is 0. My upper bound becomes infinity while I approach infinity, and my lower bound when I plug in tan of 0 is still 0. And this is just 2u du, and this just becomes u plus 1 raised to the power of 4. Well, okay. We still have something raised to the power of 4, so we're still not done yet. But I could do something a little bit better. I can make another u substitution. I can say, let u plus 1 be equal to some t. And this is a very easy substitution to make. So in this case, du is equal to dt directly. And if I solve for u, that just equals t minus 1. So let's update this integral. So infinity plus 1, that's still technically infinity. I'm still approaching infinity. 0 plus 1 is 1. So now my lower bound is changed to 1. All we did is basically just translate this function all we basically just did is just translate this function 1 unit to the right, basically. Now I can, for u, I can sub in t minus 1, and since my du is directly dt, I can write that. U plus 1 was t, so t to the power of 4. This is very good because now I only have a single term on the bottom, and I can break this up as follows: 2 t to the 3 minus 2 t to the power 4 dt. So I could take the 2 out, and it's pretty easy to integrate this. Negative 2 minus this. And these are just the antiderivatives. and infinity and 1. And I can't really plug in infinity, so I'll take the limit. So if I look at this term a little bit more carefully, I have negative 1/2 t squared plus 1 over 3 t cubed. So I'll just take the limit for the top part as t approaches infinity. And if I see this, as this approaches infinity, the denominator becomes so large. And whenever this happens, this entire term basically becomes negligible and it kind of heads towards 0. Same thing right here, heads towards 0. So the limit of this function is actually 0. So I'll write that in. Zero minus, now just plugging in 1, that's negative 1/2 plus 1/3. And you get 0 minus so there we get our final answer of 1/3.